just remind you of kind of where we left off. We were talking about particles and waves, and we said, yeah, particles are very different than waves. Particles are localized and waves are spread out everywhere. And we're going to sort of delve a little bit more into the differences because we're going to be talking a lot about waves and wave type equations. But first, let's go back and talk about light. Newton thought light was particles, and that something was emitting light would be shooting particles and they were captured in your eyes. And that's kind of nice because it neatly explains why things cast sharp shadows, at least when you have a nice point-like source of light. But we know from our introductory physics stuff and, from the waves course, presumably, that light displays wave-like characteristics too, and the properties that we use, or the words we give to why it or how it demonstrates its wave-like behavior are, one is diffraction, and that means that if we had a bunch of particles going through an opening, this is supposed to be water waves going through, I don't know what you call this thing, but the thing that breaks the waves near the shore, so you don't have such great waves where the boats are coming in and out. And here's a little passage where the boats can go in and out. When a wave comes through there, it bends. Instead of it doesn't just travel forward and give a sharp shadow along the lines of the obstruction, but it bends inward. Here's a water tank with a little opening in it, and you can see the wave diffracting it. So it bends around corners. It doesn't just keep going in the same direction it's going. And the one we do the experiment with in Physics 230 is interference between two waves. In other words, we do Young's double slit experiment. You send a light wave through two adjacent openings, and the openings are small enough and close enough, you'll see constructive and destructive interference. So you get maxima and minima of the brightness on the screen behind. So this again is a water wave demonstration, but it's showing here's presumably some physicist who's taking two balls and bouncing them up and down sinusoidally in the water, and you can see redirections along which there's going to be destructive interference and constructive interference in the waves generated by the two balls that he's bouncing up and down on the surface of the water. So that Young's double slit experiment and other experiments where you can demonstrate diffraction show that light is wave-like. And so in the 1800s, it was well accepted that light was wave-like and matter was particle-like. In other words, people thought that matter was made of small, we were beginning to develop the atomic theory of matter and understand that it was made of tiny little pieces. In other words, matter didn't seem by itself to have anything intrinsically wave-like about it. Now, considering light again, you'd think that if you shone light through a double slit and you turn down the intensity, what would happen to the pattern that you're seeing on the wall behind it? Well, if you turn down the intensity of this laser beam, I would expect that this pattern would just get more and more, and it would just fade and get less and less distinct, but it would still be continuous on the wall behind the double slits. And generally you will see that unless your experiment or the pattern, your detector on the back wall is very sensitive, you're just going to see it fade away to nothing. But if you have a very sensitive detector, then you'll actually see that that doesn't happen and something different happens. We can detect individual photons coming through. So let me show you a little kind of cheesy simulation. It's one of these PhET simulations that you've probably seen with Dr. Neiser before. This one's especially cheesy because it's got a ray gun looking kind of thing that's supposed to be the laser beam. And it used to work a little bit better than it does now, but we'll try our best with it. So it's supposed to, the idea is I can choose the color of my laser beam, the wavelength of it, and I can turn on the laser beam, and the laser beam would form a pattern on the screen. And of course, it's just a single bright kind of region. If I don't have anything in the way, I can put the double slits in the way. And if I were imagining that this light beam is made of particles, I would expect to see a bright spot here and a bright spot there. But of course, I see the Young's double slit experiment kind of pattern behind, with a central bright peak and then various order bright peaks going off as I go to the side. Now, if you have a very sensitive detector, and this isn't the best illustration of it, but it was the best one I could find, and I turn on the laser, instead of seeing a continuous brightness on the back screen, you'll just see an individual part of the screen light up in a very definite location. And if I keep the laser on, it shouldn't be showing it like pulsing discretely like this, but actually the laser's on continuously, and I'll see individual bits of light collect on the detector behind if we show where they appear. And if you keep doing that, you would see eventually those little bright spots would approximate the bright pattern behind. And if I put the double slits in the way, clear the screen, and I keep firing this thing, I'm not going to do it because for some reason this runs really slowly. If I kept doing this, I would find, if I keep track of the locations of the bright spots that appear on the screen behind, that even though it looks like we're detecting on the screen something that looks like individual particles, if we did this for 1,000 until we got 1,000 bright spots on the screen, we would find the distribution of those bright spots approximate the Young's double slit experiment there. So going back to the slides, what that means is that light seems to have both particle-like aspects. That's the individual, it seems like the light is delivering its energy and momentum to a particular location on the detection screen. That's given by one of these little dots there. And yet, if we collect a lot of information for a lot of particles as they go through, they seem to be interfering with themselves and still creating a double slit kind of experiment if we send them through a double slit like that. And so the question we want to address now is, hey, there would be a nice symmetry since light is both wave-like and particle-like. Wouldn't it be nice if matter were both particle-like and wave-like too? Would give a nice symmetry, but it also might solve that atomic stability problem, the stability problems we mentioned at the beginning of the course. And de Broglie, as you know from modern physics, was the one who proposed that without really a theory to back it up, other than just saying, hey, I'm going to make some rule about how wavelengths correspond to momenta and how energies correspond to frequencies of the wave. Okay. So de Broglie said matter is a wave. He's not going to tell us very much about the wave, but he does tell us about the wavelength and the frequency depend on the state of motion of the electron or the proton, those particles that were known about at the time. Okay, so as you know, this is MV. We're talking about non-relativistic particles now, his theory applies to. So MV is the momentum. So this is the relationship, from modern physics, P equals H over lambda, if I solve it for MV. And then energy is related to frequency. You might have called this nu in modern physics. So this is saying E equals H nu, which hopefully at least rings a bell for you. So he's postulating those two relationships for the waves. And what he realized, the motivation behind postulating this, is that you could think of the orbits in the Bohr atom as being just the right radius to fit an integer number of wiggles, of wavelengths of the wave as it's going around, whereas for forbidden orbit radii, a wave wouldn't fit around with an integer number of wavelengths in there. Okay, that's a fine theory, but the amazing thing is the experimental detection of these wave properties. And this is what you learned about is the Davison-Germer experiment, where electrons were fired at a nickel target and they had a detector that they moved around to different angles and found that the amplitude of scattering actually was related to the angular position and depended on the spacing in the nickel target right there. And unfortunately, I was going to show you a demonstration of something related today in class, but I'm just going to show you some images of it. This is what I set up at the end of the day yesterday to demonstrate in class today. We have one of these, and when we were moving out of Olin Hall, I found this thing, and nobody really knew what it did, but I sort of looked it up, and it's an electron diffraction tube And so what you can do is, it's like a cathode ray tube. You know, the old TV tubes are the ones you use for the E over M type of experiments. I assume you use something like that in modern physics. You can deflect the beam in different directions with these controls down at the bottom. And inside this vacuum tube, so there's a phosphorescent screen on the front, so you can see where the electron beam is hitting, and I can direct the beam, you know, to different parts of the screen here. That's not very interesting so far, but inside the tube, there are a few different pieces of material. One of them is a little thin wafer of carbon, actually a single crystal of carbon. So there are carbon atoms in a little crystal, and there are some other targets too, but the carbon one's the most interesting. And if you move the electron beam so that it's hitting that carbon target inside there, and then you look at what you see on the screen after you do that, you see something that looks much like an X-ray diffraction pattern, except an X-ray diffraction pattern is for light or electromagnetic radiation, right? This is kind of amazing because this isn't light coming through, this is electrons interfering with themselves as they pass through a thin wafer of carbon atoms. And where we see those bright spots are kind of like the constructive interference locations for an electron passing through a whole lattice of carbon atoms. In any case, it's showing that electrons do have wave-like properties. And so that completes this kind of symmetry, which is what de Broglie was going after. He was a philosopher and he liked things to be symmetric. And so with almost no evidence, postulated that it would be nice if things were this way, and then experimentally it was found to be true. So that's a nice symmetry. Light and matter both have wave and particle-like properties. And this is really the focus of our course, quantum mechanics here, that we're going to study the wave-like properties of matter. That's what we need to learn quite a lot about. And we're going to be interested in non-relativistic quantum mechanics. If you go on to graduate school in physics, you'll have the opportunity to take a course in relativistic quantum mechanics. So we're only going to look at massive particles moving at speeds which are much lower than the speed of light. So in particular, our theory is not going to describe photons, which always travel at the speed of light, or at least light pulses travel at the speed of light. And nor is it going to describe the interactions of photons with matter. And to do that, we need relativistic quantum mechanics, which is a theory like quantum electrodynamics, which maybe you talked about a little bit in modern physics. And it's quite a bit more complicated to calculate with than non-relativistic quantum mechanics. So maybe you'll get a chance to take that in physics graduate school. All right, so we're going to delve a little bit more because we're talking about matter being a wave. And we want to delve into, when we say it's a wave, well, we've already learned probably about the wave equation in physics 240. And the Schrodinger equation is different than a wave equation. So we want to delve into it a little bit just to get a context for it. What's different about the wave equation you learned about in physics 240 and the Schrodinger equation, and what makes them similar? What differences do they have? Okay, so yes, de Broglie defined a wavelength for a particle in motion, but real wave motion, like the water picture I've got down here in the bottom, is seldom sinusoidal. It doesn't look like a traveling wave. It's just sort of bouncing up and down randomly. And it's not completely random, of course, but there's nothing that looks like a traveling wave to it. If I asked you what the wavelength of this water is, there wouldn't be one sensible answer. So de Broglie wouldn't know what to say about that. Can matter be in other wave states with no definite wavelength? The answer is yes, but de Broglie had no idea how to describe that. And so that's what we're going to delve into in physics 399, how to completely describe the wave behavior of matter and relate it to the particle kind of behavior of matter that we see when we make a detection of individual particles. Okay, so continuing, remember I had 5 different areas we were going to talk about at the beginning. We're into the second one now, which is what is a wave? Properties of traveling wave solutions to the classical wave equation. Okay, so we just said a wave, when we think of a wave on the surface of a pool, it doesn't have to have a definite wavelength. So what do we mean by a wave then? How is a wave related to other things that may not satisfy the wave equation? Well, at the very least, when we're talking about a wave on the surface of the pool, its amplitude might be a function of x and y, and it certainly depends on time too, as the wave bounces up and down. So it would be a function of x, y, and t. If we have a wave going through three-dimensional space, not on a two-dimensional surface like this one, it might be a function of x, y, z, and t. So the amplitude, we might write that way, or the height of the wave. In quantum mechanics, as you know, we use the capital Greek letter psi to denote the amplitude of the wave that's going through space. It represents the particle. Okay, so capital Greek psi. Remember, can I just grab this and move it? Yeah, okay. I'm not crazy about where this thing is. Okay. So if you've got a wave traveling along the x-axis only, of course, our wave function psi would just be a function of position x on the axis and time for motion in one dimension. But specifying this wave equation is not enough. In other words, I could give you any function of x, y, and z and t, and some of them wouldn't be justified in calling them a wave. In other words, maybe my function of x and y and t might look like this. In fact, I've chosen one here that has a particular shape as a function of x and y, but it doesn't depend on t. It doesn't seem like there's anything wave-like about it. So we wouldn't necessarily want to call this description, even though it's the kind of description we want to make for a wave, we wouldn't want to call it a wave. So we need something more than just that function. There's nothing wavy about it. What's going to determine how that function wiggles and jiggles in time and whether we're going to call it a wave? And that is, we need a partial differential equation that's called a wave equation. And since even for a wave in one dimension, that psi is going to be a function of x and t, we need at least two variables that psi is going to be a function of. And so if we're going to write down a differential equation, we have two different derivatives we can take with respect to psi. We can take the x derivative and the t derivative. And of course, if it's in three dimensions, we have y and z derivatives too. So there's many partial derivatives. And that's why if we form an equation out of these, we call it a partial differential equation. I'll just abbreviate that as a PDE. And I assume in your math courses, you don't learn much about PDEs. We do talk about them in physics. You probably saw it in modern physics where you talked about the Schrodinger equation and maybe the wave equation. And certainly you saw partial differential equations in physics 350 if you took that with me last time. Some of you were in there. Okay, so for classical waves like sound, waves in a string, light traveling through space, the amplitude satisfies what we call the classical wave equation that you probably learned about in physics 240 down here. This is for waves traveling in three dimensions, okay? And we have the second partial derivatives with respect to the spatial variables added together, and that's 1 over c squared times the second partial derivative with respect to time in three dimensions. This combination over here, and we'll use this notation in this course, is called the Laplacian. In other words, the Laplacian operator is the second partial derivative with respect to x plus the second partial derivative with respect to y plus the second partial derivative with respect to z. And that whole operator is being applied to psi over here. And so we just write that briefly as the Laplacian of psi. Okay, so that's one way, compact way to write the classical wave equation. Just to get some intuition about this wave equation, and so I can ask you a few questions to develop our intuition, let's stick to one dimension. In other words, I'm going to imagine a wave traveling along a string in one dimension, right? We're wiggling a guitar string and a wave might be bouncing around on that string. And so there's no y or z derivatives to talk about. Psi is just going to be a function of x and t, and that's going to tell us in this context the amplitude of the wave. So in one dimension, the psi is going to represent the height or amplitude of the guitar string as it goes up and down. And it's going to be a function of position x on the string, and it's also going to change with time. So there are derivatives with respect to time and position. So one way to think about this, to get a little bit of intuition, is looking at this. I can think of the second derivative of psi with respect to t. That psi represents the height of the guitar string, right? Psi represents the height of the guitar string relative to its equilibrium position. And so the second derivative, if psi is the sort of height of it, that means psi is the position. D psi dt would be the velocity of the height. In other words, the rate at which the height of the string is changing at a particular position. And the second derivative of psi, second derivative of position with respect to time, is the acceleration along the vertical direction. So at a particular point, d squared psi dt squared is how fast that string is accelerating vertically. And of course, the second derivative of the height with respect to x, we usually call the concavity of the string. So if the string is going up and down at a particular instant, there would be points of negative and positive concavity, using the language of calculus in there for a function of x. So this equation, the classical wave equation, says the height, the acceleration of the height or the amplitude of the wave is proportional to the concavity. And let's just try to dig into that a little bit more, and so we at least know how to think about these partial differential equations, because you don't end up using them really at all, as far as I remember, in any of your math classes. It's just in physics classes. So here I'm going to imagine a very particular solution to this classical wave equation, and it's a sinusoidal traveling wave. So I've got a sinusoid here. So we're imagining this is my guitar string with a really exaggerated amplitude. I've taken a photo of it at a particular time, and the guitar string is stretched along the x direction. And this particular wave happens to be moving to the right as a function of time. So you see the velocity indicated here. So all these peaks and valleys are going to be traveling to the right as time goes on. And what I want to do is compare the acceleration at each point to the concavity, just to get a feeling for how to think about this partial differential equation in one dimension. It's not the Schrodinger equation, but at least we'll get some idea of how to think about this. So let me just, if I can ask a few of you for just shout outs on some of these things. Let me just ask you, so here it is, at this instant, the string looks like this, but I'm also telling you, as time goes on, it's traveling from left to right. So remember, the individual bits of string are not moving from left to right? Your guitar string is actually moving up and down everywhere. And if I asked you at this instant in time, where this piece of string happens to be right in its equilibrium, neither up nor down position, but the wave is moving to the right, what is the sign of the string velocity, or direction, being up or down? Or is it not moving at all? Anyone want to shout out whether the string at this instant at which I've taken this photograph for the wave traveling to the right, at that location right there, is the string moving up or down, or is it momentarily at rest? Anybody have any idea about it?
I would say it's moving up.
And what's your reasoning, Alvis?
Well, if we look at the peak immediately before that, it's up. And then assuming that the wave keeps moving, the peak, the actual presence of a peak would be moving to the right. And the only way for that to work would be for that place in the center, or at x equals 0, to rise up.
Right. I think what Alvis is saying is that when he says before, ahead of it, I might have said behind, but he's saying that this whole shape is moving to the right. So this position right here is soon going to be over here. And that means this bit of guitar string is going to have moved up, right? And therefore it's heading upwards at this particular time. So I'm just going to draw that on there as an arrow. String velocity I'm drawing in green here. How about this position that's sort of a little bit below it, not quite to the bottom trough there? What do you think about the string velocity there? Somebody else was volunteering before. I want to tell me what you think about that. Up, down, or staying constant?
It's also moving up.
It's also moving up. Do you have any way of reasoning whether it's moving up faster, slower, or the same rate as this one right here?
I think it's moving up slower.
Yeah, I mean,
Yeah.
it might help to think about, well, as you get down here, I think it's pretty clear that, in the next instant, it's not going to be moving up or down, right? Because you're sort of on a locally flat spot. So it's going to go from this and then down to this. So it's actually moving upward a little bit more slowly there than it would have been here. And it's related. It's not hard to see that it's related to the slope of this, right? The rate it's moving is related to the slope of the string there. So the slope is just a little bit smaller right here, and therefore the rate it's going up is a little bit less. Not surprising, the string velocity maybe right before we get to the minimum is really small, right? Because we're getting to a point where the slope is getting smaller. How about over here on this side? Makai, can you see if its string velocity is going to be up or down there?
So that'll be going down.
Yeah, it looks like it's going down because the part of the string immediately preceding it is a little bit below, and that below spot is going to move over to the right as this whole shape moves to the right. So it's going down again because of the sort of shallow slope there. I drew this as kind of a small arrow going down. Here, not surprisingly, it's still going down, but it's larger, not to belabor the point. And then it gets a little bit smaller as the slope gets smaller up here, and so on. Okay, so we could reason through each one of these, but we can this was just as a warm up to think about the velocity there over an entire wavelength of this particular shape. Okay, now we're not concerned so much about the velocity. I wanted to think about the acceleration, and we might be able to use the velocities to think about the acceleration at these particular points. Can you think about using the relative velocities of these given points here, what the acceleration, both the sign, if we call positive up, right? So positive acceleration would mean it's accelerating upward, and how much it's accelerating. Well, let's just think about the sign of it. Is the sign of the acceleration, meaning upward is the positive direction, downward is the negative direction. Is the sign of the acceleration for this point at this instant in time positive or negative?
It's negative.
And what's your reasoning for that, Albus?
Because it's being basically, this is more of a mathematical interpretation, but the acceleration would just simply be the graph we see currently, except mirrored across vertically. And then if it were to be
I mean, what I was thinking, I think you're thinking how various derivatives of a sinusoidal graph would change. I was thinking,
yes.
If we say the acceleration is the rate of change of the velocity, right? Is the velocity trending more in the positive direction a moment later or more in the negative direction a moment later on the string as this wave moves to the right?
Oh, then I would say it has a, actually, no, wait, it has a positive acceleration.
Yeah,
To put it
because
into
a moment later, it's going to have this velocity, right? So its velocity is positive and it's going to become more positive. That's a positive acceleration.
Or to put it into a physical explanation, because the acceleration, the position is being forced upwards.
Yes. Okay, so that position is positive, and I'm just going to, not worry too much about the magnitude of the acceleration, but just show at least the sign here. So at that point, the acceleration is positive. What about this? Jake Woosley, what do you think about that one? Sign of the acceleration, if positive is up?
Wouldn't still be positive for the
still positive, because a moment later it's going to have this velocity. So its velocity is positive and it's becoming more positive. That's the hallmark of positive acceleration, right? Good. How about over here on this side? Riley, you want to help me think about this? Would the acceleration here be positive or negative if we consider that it has this velocity now, and a moment later it's going to have this smaller downward velocity?
I want to say negative, but I'm not sure.
Yeah, so so right now, notice that this point is moving in the negative direction. So it has a negative velocity, right? If its velocity became more negative, I think everyone would agree that it has a negative acceleration because it's going faster and faster in the negative direction, right?
Mhm.
But instead, it has a negative velocity, but it's actually slowing down in the negative direction. In other words, it's trying its best to trend towards the positive velocity direction. It has to slow down in the negative direction before it can start going in the positive direction. So is it clear that this point is, though it's going downward at this instant, a moment later, it's going to be going downward with a slower speed. And that means it's slowing down in the negative direction. This is what causes so much confusion. You know, I'm teaching Physics 110 also this semester with Physics 110 students. It's just maddening to think about acceleration when things are moving in the negative direction. But slowing down in the negative direction is a positive acceleration component. Is that okay? Or any questions about that with anyone? So I'm going to put a little plus sign there, even though that's definitely more confusing. The same is true for these other points. We could reason about them. Even at the bottom here, we would say, you know, a moment before the instant when I took this picture, it was moving downward. And a moment later, it's going to be moving upward. So it's clearly accelerating in the upward direction. That's a positive acceleration. So this is a region of positive acceleration. How about over here? Who am I forgetting about? Tanner, maybe you can help me think about this one here.
Would it be negative?
So in this case, yes, it has a negative velocity, and a moment later, it's going to have a larger negative velocity. That means it's accelerating in the negative x direction, right? So there's a minus sign there. And not to belabor the point, but we're going to find out that over here, you know, has a positive velocity, but a moment later, it's slowing down in the positive direction. Slowing down in the positive direction is also a negative acceleration. It's the same way all the way through. All right, that's enough about that. What I've succeeded in showing here is that the string acceleration is positive here and negative there. We're trying to compare the acceleration to the concavity. Does that match up? In other words, what's the concavity in this region? If we remember that notation from calculus, positive or negative concavity?
It's positive concavity, right?
Positive concavity, when it concave up, means it's, you know, opening in the upward direction or holds water. Negative concavity is where it's opening downward or wouldn't hold water, right? So that agrees with this. C squared is a positive constant. So this is saying the height acceleration is proportional to concavity. So, you know, if you think hard enough about these kinds of differential equations, you can really get some intuition about how these things are going to evolve as time goes on. And this is a very simple example where we did a traveling wave. The same thing is true for even complicated solutions. When you see, you know, you pluck a guitar string, but it's not vibrating sinusoidally, but it just has sort of a random motion to it. At each point, the acceleration of the height is going to be proportional to the concavity. So we can at least get some idea of what it's doing. Any questions about that? We're going to have a harder time applying this to the Schrodinger equation because there are complex variables involved there, but at least you have some idea mechanically of how partial differential equations tell us that things are evolving as time goes on. It's more complicated to think about if I have X, Y, and Z variables, and all the more complicated if there are I's in there, but it seems to be matching, at least in this case. Okay, so that was just kind of a demonstration of how to think about that, because we really need to get used to thinking about these functions of X, Y, Z, and T, or at least X and T. And, you know, most of the time we're not so familiar with it. All right, let's develop some properties of the the one-dimensional classical wave equation. One of the things that you might, I don't know how much your professors talk about this in math. You know, I took as an undergraduate, I had to take a partial differential equations course, but here there is no such course, but you may have heard of linear versus nonlinear ordinary differential equations in what is that, 360, math 360, 361? I can't remember anymore.
360
360.
differential
So
equations.
you probably talk
correct?
about linear versus nonlinear ordinary differential equations. Here we're concerned about whether or not this partial differential equation, this CWE stands for classical wave equation. I will use a handful of acronyms for things throughout the course, or just abbreviations like this. It's not going to continue all the way through the course, but you know, writing classical wave equations is sort of a pain. Okay, so it's linear. Let me end my show here and now bring up the first of the worksheet problems. Let's go all the way to the top. This is the worksheet that, you know, now that we're having, that I didn't come today, I really wish I would have handed it out, at least in class. But here's our classical wave equation in one dimension for one-dimensional waves, right? That we just looked at. C is a constant. We're going to talk about how it's related to the speed a little bit later, the phase speed, how fast those peaks and valleys would move for a traveling wave solution. Okay, so any solution is going to be some function of x and t, and we're going to be concerned about how those, one property of those solutions, and that is, this is a linear partial differential equation, and linear means the following things. Partial differential equation is linear if given any two solutions to it, then you can take any linear combination of them. That means a constant. So here I'm going to imagine that psi1 as a function of x and t is a solution to this partial differential equation, solution to the wave equation, and psi2 is also a solution. And now what we want to prove in this, and it's actually fairly straightforward to prove, is that any linear combination of psi1 and psi2 is going to be a solution to that partial differential equation. So we want to show that this is true, what I'm circling right here, that the combination A, where A is a constant, times psi1 of x and t, plus B times psi2 of x and t, where B is a different constant, that it satisfies the classical wave equation. And we're going to take as our assumption that I know that psi1 satisfies this equation, and separately psi2 satisfies this equation. Okay. And usually when I've done this worksheet before, either it's pretty clear to people at the beginning or it's horribly confusing as to how to proceed. But what I'm going to do is just start chipping away at this left-hand side. Let's begin with this left-hand side of what we want to show. We want to show the thing I'm circling, and let's try to make it morph into the right-hand side. So here's the left-hand side of the thing I want to show. I'm going to assume that psi1 and psi2 satisfy this differential equation, and we're starting with this. I've got a second derivative with respect to time of this mess. And we know that derivatives can distribute over plus signs. In other words, a derivative of a sum is a sum of a derivative. And a derivative of a constant times a function is the constant times the derivative of that function. In other words, derivatives move right through the constants a and b. So I can first distribute this second derivative over the sum, and then I can move the constants a and b out of those second derivatives. That's the first step there. And now I'm going to use the fact that psi1 and psi2 both satisfy this differential equation. So a second derivative, oh, I'm sorry, this should, I see an omission here. This should have a 1 subscript on it, just like this one has a 2 subscript on it. Somehow I lost the 1 there. The second derivative of psi1 with respect to t is c squared times the second derivative of psi1 with respect to x. So I'm making that replacement over here. And same thing with psi2. I can make that replacement with psi2. And then I can factor out some common things, right? The c squared appears in both of these. and the second derivative appears in both of these, and I can undistribute that second derivative over the plus sign and factor it out. And what's left in parentheses is a times psi1 plus b times psi2. And so if you look at the beginning and the ending place, what we've shown is equal is actually this differential equation. All right, big whoop. What that means is if you give me two solutions to a partial differential equation that's linear, I can give you an infinite number more, right? Because I can take any linear combination of those two solutions and it's another solution. That's called linearity. So when you hear a math person talking about a certain linear differential equation, whether it be ordinary or partial, it means linear combinations of solutions are solutions, okay? Now, a note down at the bottom says a special case of linearity is the superposition principle. Superposition principle says that if you have two solutions to a differential equation and it's linear, then the sum of those two solutions is also going to be a solution. And we know that from our wave solutions, right? If I've got a wave, a pulse wave to a wave equation, that a pulse traveling to the right, and I've got a pulse traveling to the left, those are two different solutions to my wave equation. Then the sum of those two, which would be both pulses traveling towards each other and passing through each other in a certain sense, is also going to be a solution. So let me go back to the slides here. Oops, lost my place, but where are we here? So here's a little GIF showing that, two wave solutions, as in a way, pulse-like solutions to the classical wave equation, pass right through each other. Well, what do you mean pass right through each other? They pass right through each other by adding together. But once they're away, their amplitudes are away from each other, they just go on their merry way. Same thing, here are two pulses down at the bottom that are traveling. They actually have opposite amplitudes. And they pass right through each other by adding together. So that the superposition principle says, if you have two solutions to a linear differential equation, the sum is also a solution. That's one property of the classical wave equation. It's linear, and therefore the superposition principle applies. Or, the superposition principle probably applies to the Schrodinger equation, and that's because the Schrodinger equation is also linear. We haven't shown that here, but we will be able to quite easily. Okay. The second thing about partial differential equations is it's easy to check if something is a solution. All you have to do is plug it into both sides and check to see that the equation holds. So let's look at that worksheet again. And again, I would have given you a chance to do these in groups in class, so it's not the best way to do this, but it's, at least we can talk through how to do this together. Okay, so there's lots of solutions to the classical wave equation. To see if a function is a solution, you just plug it into both sides. Here is a function of x and t. There's no guarantee that this function that I've made up here is a solution to the classical wave equation. So what I want us to show is it a solution? Prove it to me. Or is it not a solution? Prove that to me. And all I have to do is plug it into the classical wave equation, compute the left side, compute the right side, and see if they're equal. So let's go to the solution now. Of course, it's more interesting if it works out. So I made it so it works out. Yes, even though this isn't a traveling wave at all, it is a solution to the classical wave equation. I'm going to compute the left-hand side. I don't have the classical wave equation written here, but this is the left-hand side that I wrote, and this is the right-hand side. So let's compute the left-hand side. Second derivative with respect to time. Let's take one time derivative of this function at a time. When I take one time derivative, I've got to do the chain rule, first do the power rule. I bring down the -2 and I get that thing to the -3. And then I take the derivative of this with respect to time and I pull out a -c when I do that from the chain rule. That's one time derivative. I've still got to do the second time derivative. So I do it again. The -3 power turns to a -4. When the dust settles, it's not complicated. You get this function right here. Similar thing being applied to the right-hand side. I get a c squared times the second derivative with respect to x of psi. And I have to do the same thing where the power rule comes into it. When the dust settles, you'll see that the right-hand side is the same as the left-hand side. So lo and behold, even though this doesn't look like a sinusoidal traveling wave, it is a solution to the classical wave equation. We just proved that it is. Questions about that? All right, nothing complicated, it's just partial derivatives there, and that's what it means to be a solution. It means you plug it into both sides and they're equal after you've taken those derivatives. Second part that we were supposed to do says, let's evaluate it at 3 different times. So I'm going to take that equation up here that we just showed satisfied the wave equation, and I'm going to evaluate it at t equals 0. That makes this middle part go away. So I get x plus 1 to the minus 2 power, or 1 over x plus 1 squared. And we kind of know what that looks like. It's going to be centered at x equals minus 1. In other words, 1 over x plus 1 squared is going to have some kind of vertical asymptote, right? When x equals minus 1, it's going to go to infinity because I have a 0 in the denominator. So it's going to have a peak centered at x equals minus 1, and that's when t equals 0. That's this one I'm showing here in the solid curve. So it's got a vertical asymptote there. I just drew it kind of like a volcano, but it's got an asymptote there. What about at a later time? What about when t equals 1 over c? That's a slightly positive time when t equals 1 over c. When t equals 1 over c, this is going to be a minus 1, and then we've still got this plus 1 over here, so I'm going to have just x to the minus 2, or 1 over x squared. That has a vertical asymptote at x equals 0. So it looks like at t equals 1 over c, a slightly positive time, it's going to have this shape. At t equals 2 over c, it has the dotted shape I'm showing here. And so it looks like this shape is traveling to the right. It's a little bit concerning because the value of this function isn't finite everywhere, so it seems kind of problematic, but all the cases that were finite were actually much more analytically difficult to take the derivative. So I thought I'd put this, one that actually has a vertical asymptote in there just because it was easier to calculate the partial derivatives for us. So the same thing would be true if we had a Gaussian thing. We could have a Gaussian moving to the right, but I didn't want to do that example because Gaussians are kind of painful to take multiple derivatives of. Okay, so as time goes on, the shape is moving to the right. Any questions on that? All right, let's go back to the slides. I guess I shouldn't have gone in slideshow mode because we're going to go back to the worksheet again. It has traveling wave solutions, okay? That's, at least in a simple way, that's the whole reason we're calling this partial differential equation a wave equation. We call it a wave equation because it has traveling wave solutions. I'm looking at my phone to make sure I don't go overtime here. Okay, so that means the classical wave equation is justified in being called a wave equation because there are sinusoidal solutions that travel this way and that. Those are what we think of as the simplest kinds of waves. If a partial differential equation didn't have traveling wave solutions of any kind, we certainly wouldn't call it a wave equation at all. So that's what justifies it being called a wave equation. Let's see what worksheet problem D is here. The solution you found above was shaped like a volcano, right? It had that asymptote, the vertical asymptote. It doesn't have a sinusoidal shape, so it's certainly not a traveling sinusoidal wave. Nearly all classical wave solutions don't have sinusoidal shapes. Remember the surface of the pool, even though we call those waves, it doesn't look like sinusoidal shapes necessarily. It's not a traveling wave solution. But all wave equations have traveling wave solutions. That's the justification for calling them wave equations at all. And that the Schrodinger equation is actually no exception to that. So that's one reason we're calling the solutions waves. Okay, so let's suppose that this function I'm giving you here, a function of x and t, let's think of k as a positive constant and omega as a positive constant. Here's a function of x and t, a is a constant too. This is a solution to the classical wave equation. Suppose I claim that that's true for any constants a, k, and omega. it's actually not quite true. You'll find out if you substitute this into the classical wave equation. This isn't a solution for all values of A, K, and omega. There's some restriction that arises. And, normally I've let you do this and figure out what the restriction that arises is, and maybe you know already, but let's plug it into both sides, right? So I'm going to take this cosine function with the three undetermined constants, A, K, and omega left in it. Just they're not functions of X and T. Let's take that second derivative with respect to time. Let's take the second derivative with respect to X and put a C squared in front of it. And let's force these two sides to be equal. And clearly they're not always going to be equal because omega squared isn't necessarily equal to C squared K squared. But it will be a solution if omega squared equals C squared K squared, right? And because we got all those squares on there, it's tempting to take the square root there. And if we take the square root, we have to think about our plus or minus rule, right? If, if y squared equals x squared, then y equals plus or minus x. Same thing here. If omega squared equals C squared K squared, then that means omega equals plus or minus CK. So this traveling wave solution, right? Now, I'm hoping you kind of seen these kind of solutions before in physics 240. This represents a cosine that's actually traveling. Well, if omega is positive and K is positive, it would be a wave equation that is traveling in the positive X direction. Jake Woosley, I see your hand up. Question?
No, that was from earlier. That was.
Oh, okay.
Yeah, I'm good.
Did you get it answered?
Yeah. Well, I did.
Okay, great. So in other words, we can't have any old traveling wave. You may be familiar with the fact that this K is related to the wavelength, right? K equals 2 pi over lambda, or lambda is 2 pi over K if we're considering this traveling wave. So K is related to the wavelength. Omega is the angular frequency, and it's related to the period. So we can't have any old wavelength and period. The wavelength and the period have to be related in a very definite way, and they have to have this kind of relation in order to be a solution to the classical wave equation. Okay. Any other questions on that? Check my time here. Good. Okay. So let's continue on. So for each wavelength, that means since K is 2 pi over lambda, each lambda wavelength corresponds to a particular K. For each wavelength, there's going to be a different traveling wave solution. And we just found if I choose a K, I'm not free to choose an omega. Omega has to be related to K in a very definite way, but I am free to choose a K. There are lots of different wavelengths solutions. Any K I choose is going to have a corresponding traveling wave solution there. That's not only true for the cosine function, but also for the sine function. And since they're individually solutions, any linear combination of them is going to be a solution. So this is our most general traveling wave solution that we can write down, as long as omega and K are related in the way we found out. Now, the question we want to address here, and this is probably something that you talked about either in modern physics or 240, is how do the speeds of various traveling waves compare? In other words, if I take a traveling wave, a sinusoidal wave that has a certain small wavelength, and I compare how fast it travels to the right or to the left with one that has a longer wavelength, are they the same? Or does the speed change with wavelength? Do you know what we call that phenomenon where speed of a wave, the phase speed of a wave, changes with wavelength or stays the same? What is that phenomenon called?
Dispersion?
Yeah, it's called dispersion. In other words, if the speed of a wave doesn't depend on the wavelength, we say it's a dispersionless wave. And if it does depend on the wavelength, we call it a dispersive wave. And so we want to find out for this particular classical wave equation, is it dispersive? And we could say the same thing about other wave equations. In other words, we're going to call them wave equations only if they have traveling wave solutions. But just because they have traveling wave solutions doesn't mean each wave travels at the same speed. And we're going to find out That's certainly not true for the Schrodinger equation. It has traveling wave solutions, but they don't all travel at the same speed. It's a dispersive wave equation. Okay, so dispersion is the phenomenon of traveling waves of different wavelengths traveling at different speeds. And in order to figure out about dispersion, we need to figure out something about, well, here I've given this in terms of K and omega. How do I figure out how fast this wave is going to be moving to the right? Does anybody just remember what the answer is off the top of their head? Maybe from 240 or maybe from work maybe in modern too.
Omega over K.
Omega over K, that's called the phase speed of the wave, but we can very easily justify that it's omega over K by noting it the following way. The phase speed means the speed at which these peaks and troughs are moving to the right or to the left. Here I'm imagining it's moving to the right. And the idea is, well, it's not as obvious in terms of K and omega, but if I talk in terms of wavelengths and period of the wave, doesn't it have to be true that if I wait one period, then this peak will move exactly over to where this peak was, right? Because if I wait one period, that means that if I sit at this location, it would have gone down and up to its same position. And that means that's exactly the amount of time that this peak takes to get over there. So the wave speed is it travels one wavelength in one period. If you think about that superficially, it might not be obvious, but then if you think about it again, it's clear it has to be true, right? And if you wait one period, this peak has to get over to where that peak is. So it traveled one wavelength in one period. Now we got to remember our relationships between lambda and K and T and omega. Most of you probably have burned into your brain by now, hopefully. K is 2 pi over lambda. They're just two ways of measuring the same thing. So for each K, there's a wavelength, and this is the relationship between them. Same thing for angular frequency and linear frequency, which I'm calling F here. Omega is 2 pi F, and F is 1 over T. The linear frequency is 1 over the period. So omega is 2 pi over T. That means that lambda is 2 pi over K, and omega is, T is 2 pi over omega, and I can substitute those in here and figure out then when I take that ratio that it's omega over K. So you may have memorized that, but it's something you should be able to easily demonstrate. And maybe we will stop there for now, and hopefully tomorrow, I'm not sure what's going to happen with the ice. The prediction or the warning was through tomorrow. And since I live in Lexington, I'm certainly not going to brave it if it looks like the ice is going to come. But a lot of times things sort of fade away. So I'm going to hope for the best and hope that I can be there tomorrow so that we can work in person. For me, it's a lot easier to have a discussion that way. But our next thing that we're going to approach is, okay, if the phase speed is omega over K, we just found a relationship between omega and K for the classical wave equation by demanding that that traveling wave satisfied the classical omega wave equation. And so that's going to tell us something about how the phase speed changes with wavelength. We'll start again there tomorrow.